Right. Hello, everybody. Welcome back. We're now going to proceed with our speaker, Mike Alvarez, professor at Caltech, and together with Jian and Yasin Kabir, presenting on studying COVID-19 pandemic misinformation and protest using social media data. So, Mike, please carry on.
Very good. Thank you. And thank you for inviting us. I'm hoping thumbs up on, you can see the slide deck, right?
That's right. And we can hear you.
Always need to check those things. In any case, thank you for inviting us to participate. And we have a lot of interesting material that we're going to try to present today. But as a basic introduction, coming after a really interesting talk on particle physics, we're going to change the substantive domain pretty radically. What we've been trying to accomplish, and a number of other research teams throughout the world are trying to accomplish, is to collect large-scale streaming real-time social media data, because it's a very important tool for a lot of the research that we've been doing. And we're actually giving a paper this weekend at SIGK-DD that goes over some of that. For example, we're interested in detecting low incident social media behavior, things like attack and hate speech, misinformation and disinformation campaigns, and importantly, how people strategically change their behavior to avoid detection when they're engaging in these kind of behaviors by the social media platforms. So collecting these kinds of data is very difficult. Pre-processing these kinds of data is very difficult, and also analyzing is difficult, largely because of their size and the computational complexity associated with collection, pre-processing, and analysis. So we're building architectures to engage in each of those three different stages of use of the social media data. And we're trying to figure out ways to easily collect, efficiently collect, and quickly pre-process and analyze these data. And so what we're going to do today is we're going to run through each of these steps. I'm going to turn over to Jian in a second. Jian is a postdoc at Caltech who's been working on developing the architectures for collection and analysis. And then we'll turn it over to Yasin, who'll talk about pre-processing. And then depending upon how much time we have left, I'll talk a little bit about some of the work that we're doing with respect to building NLP tools that work on these very large data sets using GPUs. And then hopefully we'll have a sufficient amount of time for some Q&A. So right now, I'm going to pass it over to Jian.
Hi, everyone. Can you hear me?
Yes, we can.
Okay, that's great. Hi, everyone. Thank you, Mike. So I'm going to talk about the Twitter monitors that we developed to collect a large amount of COVID-19 tweets. The COVID-19 pandemic is one of the most popular topics on Twitter since March 2020. In the peak hours in August 2020, there are on average 250 COVID-19 tweets were posted online every second, which is around 1 million tweets per hour. So to be able to conduct a comprehensive yet time-sensitive analysis, we need to collect as many tweets as possible in near real time. To achieve that, our Twitter monitor needs to be fast enough to collect and save every tweet that were pushed over from the Twitter API, and also need to be failure tolerant to minimize the offline time and maximize the data collection. So our team built a cloud architecture that is fast in ingesting tweets and robust to errors, system failures, and network fluctuations. This architecture can be deployed on any popular cloud platforms. Here we use GCP as an example to describe our Twitter monitors workflow. So as shown in this figure, the Twitter monitor has 4 parts. The first one is data producer, then the streaming surface, and consumer and storage. So we use, in the beginning, we used a high performance virtual machine on GCP to request the tweets from Twitter API. Then publish them in GCP's streaming service called PubSub. Next, we use data flow to extract the tweets from PubSub and save them into files in cloud storage. In the end, another virtual machine transfers the data files from cloud storage to Google Drive, which is shared with the research team. This architecture takes advantage of GCP's high performance and smooth data pipeline to make sure tweets are ingested and saved instantly, so that in the peak hours, there are no tweets waiting in the line, which minimize the risk of disconnection. Also, in addition, the cloud services suffer less from power outages and the network interruptions, which makes the Twitter monitor more stable. Moreover, using the streaming surface as the first layer of protection, cloud storage as the second, and the Google Drive as the third, the monitor can retrieve data from the previous steps if any error happens. So the code to deploy this architecture on cloud platform are available on GitHub. Next, let's have an overview of the COVID-19 Twitter monitors that we have been using since early 2020. So we deployed two COVID-19 monitors. One used a static keyword list that was selected by our research team, and the other is using a dynamic keyword list managed by Twitter. The first monitor, the static one, was launched on January 31st, 2020. And the keywords include coronavirus, COVID-19, pandemic, face mask, and many related hashtags. And some of the keywords are outdated from the current point of view. And we found the data collected are increasingly overlapped with the second monitor. So we stopped this one on June 30th, 2021. This monitor collected around 1.9 billion tweets, which is about 8.5 megabytes in size. The second monitor uses the Twitter COVID-19 lab endpoint and was launched on June 1st, 2020. The keyword list is managed by Twitter and is dynamic. The keywords include more than 500 topics in multiple languages. The representative ones are COVID, corona, mask, pandemic, PPE, lockdown, quarantine, hand sanitizer, and many others. The monitor is online since then and has collected around 5.7 billion tweets, which is about 30 megabytes in size. So in the next slide, we visualize the activities of the monitors in the following, in this figure. So we show the daily number of the tweets collected by each Twitter monitor. The blue trend is the static monitor, and the red one is the COVID-19 lab monitor. So we can see a quiet start in February 2020. Then the topic went viral in March, then gradually slowed down in May. After the second monitor was launched, because of the larger keyword list, we started to collect more data. Then the peak happened in August 2020. After that, the COVID conversation keeps declining, but it never despairs. Now we can still collect around 5 million tweets per day. Overall, we have collected around 40 megabytes of COVID-19 tweets, which is a big challenge for data processing and analysis. Okay, so that's it for the overview of the data collection. I'm gonna give it to my colleague Yasin to talk about the data processing. Thank you.
Thank you, Jian. I hope you can hear me, right?
Yes, no problem.
Absolutely.
Okay, thank you. So, so I am Yasin. I am going to describe how we processed a large amount of tweets that we have collected using RRoCCET packages. So one of the primary challenges to process and explore huge amount of data is the processing speed that it is required. Now, parallelizing the processing over multiple CPUs can solve this issue. However, getting a CPU clusters with lots of cores is actually costly. Now, GPUs can help us here to speed up the whole processing thing. And I think it is much less costly compared to having a similar setup with CPUs. So, and this is where RRoCCET comes into the play. So to give an idea, RRoCCET is an open source software libraries developed by NVIDIA, and it is use NVIDIA CUDA primitives that enable the low-level computation and optimization over GPU, and that can help us to parallelize the whole data processing things as well as different machine learning algorithms and methodologies. And we can also run it over multiple GPUs, and it can process data as a chunk in a single GPU also. Next, please. So this is the brief outline of the workflow that we have used for processing all of those terabytes of data. Now, although we have used GPUs, still we have to use some of the processing over the CPU. The reason we have to do that is that for loading the data and doing some of the replacement before GPUs can read and see this data correctly, we have to process some of the tasks as CPU. And those processing basically involve like extraction from zip file and then pre-processing for JSON loading and do some kind of data or attributes pickup from the JSON file. And after that, the data is directly passed to the GPU. And in the GPU pipeline, we have used DAX, cuDF, and cuDF, cuML, cuPy, and TensorFlow library for various processing, filtering, and topic modeling with some of the principal component analysis. And DAX cuDF is basically provides us an framework where we can use multiple GPUs and we can run parallelized processing over the GPU. Next, please. So to give more information, so first is data cleaner, and this step we have performed on CPUs, and we have CPU with 128 cores. And then this step actually involved the I have already talked about it. It's involved loading JSON file, selecting a specific attributes from the raw tweet text, such as the tweets, the username, user ID, and the tweet ID, stuff like that. And then the data is stored into the storage for the further processing over the GPU. However, instead of storing in the storage, we can also load the data directly to the GPU by passing it. And next, please. So after CPU processing is done, then we are going to process everything else in the GPU. Now, here what we are doing is based on our goal, we need to filter the specific tweets from a specific user or from a specific type of tweets. Now, for example, we wanted to get the tweets from US congressmen and from all other verified users. Now, if you think like that, there were around more than 400 million tweets. I mean, it's kind of rows of data which needed some duplicate removal, some other information clearance. Now filtering all of those tweets and getting some specific data points is very difficult, and it took large computational time. So we are doing all of this stuff in the GPU. We are removing duplicate words, we are removing duplicate entities, stop words, and we are clearing hashtag, mention, etc. for our further processing pipeline. And here we are using Rapids library as well. And to give a perspective how much this was speed up whole processing is that for 1 million tweets, we were able to filter, process, and remove the string or process the strings in just 3 seconds of time. Next, please. So after tweet filter and processing is done, we wanted to extract the trophy or explode the trophy. Now, for doing that, we used some of the methods that we can adopt or use over GPU. Rapids library already provides us a good amount of library and methodologies that we can run and execute over GPU. For example, word vectorization, principal component analysis, or incremental principal component analysis. And after that, for other methodologies like to extract the topics using LDA and to run the related arithmetic operation, we use Kovi. And finally, we also wanted to see how we can cluster the tweets so that we can see that top or frequent word or the trending topics that's going on over the cluster. So Rapids also provides a built-in system for that. And for example, we can use k-mean clustering with variable number of cluster, and give an idea. We are when we are testing over 500K tweets, and we are able to cluster them into 10 groups is only 293 milliseconds. So if you think about that, it is really a great amount of speed up compared to traditional clustering over CPU. So finally, this is just a brief comparison to give an idea how much speed up we were able to get compared to CPU versus GPU. So when we process everything and filter out the tweets and some other steps, we had finally around 265 million of tweets. And to get those tweets, we had to process around 11.5 terabytes of data. So for the filtering steps, which involves filtering specific tweets by the user and by other information, as well as some string processing, we were able to get up to 43x speed up compared to the CPU. And here we were using CPU with 128 core. And compared to that, for the GPU, we are using a single A100 GPU, which has 80 gigabyte of GPU memory. However, we didn't have to use all of the memories. We were using around 30 gigabyte of memories only for this, and it was able to do everything by that memory constraint. So for topic modeling thing, we were able to get up to 107x speed up for 1 million sockets. So yeah, so that's all from the Rapids perspective, and how we were able to process all of our data. So now I am going to hand over the presentation to my colleague Jian again. Thank you.
Thanks, Yasin. So at this point, we've talked about how we can collect these data using cloud-based architectures very quickly, very reliably, and very efficiently. Yasin talked about using the Rapids architecture to do pre-processing and some preliminary types of NLP, in particular topic modeling. Now, what we're currently working on, and we had hoped to have some final results for this presentation today, but we're about a week off of that. But what we're working on right now is developing tensor-based NLP methods. There has been some discussion of this in the literature, and we're working right now to make these tensor-based NLP approaches, in particular LDA and the joint sentiment topic model, much faster, more efficient, and optimized to use on GPUs so that they can very quickly analyze these very, very large scale data sets and extract, interesting lower dimensional information from them that we can use for further analysis. Typically, topic models are estimated using expectation maximization, which I think you all know is incredibly slow and very, very computationally complex. And that's in some ways hampered, I think, the deployment of those kinds of NLP topic model tools in large-scale data sets like this. But my co-PI, Anima Anandakumar, and some of her colleagues have worked to show that you can use spectral decomposition of the lower order moments to recover the same types of parameters using kind of a methods of moments approach for topic model techniques like LDA and JST. These method of moment algorithms are much, much faster than the traditional use of EM and other approaches for estimation of these kinds of models. And what we're doing right now is we're as Yasin kind of pointed to in his part of the presentation, is we're working to build easy to use Python libraries for tensor-based estimation of LDA and JST that will be optimized for use on GPUs. And those are going to be available real soon. And we're going to implement them in TensorFlow, so there'll be a very direct connection between Rapids and the TensorFlow libraries. These are some preliminary results from one of our PhD students at Caltech, Danny Ebanks, who's been working on these techniques. And it just gives you a sense for how much quicker, and this is on a very small data set. This is a data set of about 315,000 tweets. But we can take usual estimation methods for LDA or JST, which take, even on a data set of this size, literally hours to converge. And we can move those into these tensor-based methods using these kind of methods of moments approaches and dramatically reduce, excuse me, the computational time, going from hours down into minutes. And so you can imagine that what we're doing right now is trying to figure out how these kind of results scale into larger data sets. Importantly, what we see also is that when we're moving into the faster implementation of the joint sentiment topic model, we're able to recover pretty much the same information, but much more quickly and much more efficiently. The coherence of the topics is nearly similar to what we see with EM-based JST, and the number of optimal topics for the two different methods of comparison are nearly identical. So we're very optimistic, and again, we should have this code and some of these tools available in the TensorFlow library really, really quickly. So just to quickly wrap, these kinds of data sets are really, really valuable for social science researchers, and they're also interesting for computer science researchers. And what we're working on, the vision here, of course, is that we want to have an end-to-end system so that we can collect these data in near real time and try to analyze them very, very quickly in near real time. And we've come close to accomplishing that. These kind of tools are going to be really useful when, as we move forward from a political science perspective into the next election cycle, where we want to look for electoral information and disinformation. They're useful in the COVID-19 data set for looking at misinformation, attack speech, racist language is being used in some of those conversations. And again, really being able to quickly analyze these data, pre-process them, collect them in real time is the goal of our research project. So with that, we welcome questions, comments, and any conversation that folks might have.
All right, super. Thank you so much, all three of you, for this very interesting talk. We do have a few questions that we'd like to share with you as we conclude here. Let me just quickly check. Sorry, getting my little act together here. So first, just a simple mechanical question. Did you happen to choose using the Google Cloud because of Twitter's close integration with GCP, or were there other considerations for choosing that platform?
We actually have built this to work on all different kinds of cloud computing platforms. We moved largely over to GCP, partly because of the tools that they provide, which are very useful, but also partly because we were able to get quite a hefty amount of computing credit from GCP through their COVID-19 research grants program, and also some very helpful input from some of the Google engineers and the Google team. So it was partly because of some of the tools, but also partly because of the great way that they facilitated research on COVID-19.
Yeah, great. I really appreciate that, because we often find that this kind of decision process really is involves interaction with the cloud providers. So it's interesting to hear that. Another question, what were the main reasons you had your pipeline write output to Google Drive as opposed to GCP file storage services? Could you comment on the trade-offs?
So I'll take that one too. Largely, it's a matter of making these data sets easily available to large numbers of people in our research team. As you can imagine, we've got quite a few students at Caltech and some partner universities, as well as some of our partners now at NVIDIA who want to use these data. And so instead of giving them direct access to our GCP setup, we like to pipe these data sets into Google Drive, where they can be really easily accessed by anyone at Caltech because of the usage of Google Drive that Caltech has, or we push them into Box as well, because then we can actually share them in a secure way more readily. It's really just an ease of use decision, largely for a lot of our end users of the data.
Cool. And while we're in this Q&A phase, I want to remind everybody that if you have questions, please do drop them into the chat so we can pass them along and make sure everybody gets questions answered. Our next question that we have here is an interest in whether the I/O performance was an issue given the huge data volumes. So do you have to be like making considerations about data format or other aspects?
Jian, you want to take that one?
Yeah. So for the GCP streaming service, there's no need to change the data format because they all use the JSON objects. So we just take in the JSON object and transfer it into binary string and then publish in the GCP streaming service. So we try to minimize any processing other steps in this step because it's the most vulnerable step. So if we read in data too slow and the Twitter API will shut down will disconnect our connection. So yeah, we don't do any format change of processing in this step, but we do it after we have them published in the streaming service.
Okay. And continuing in that vein, we have some other nuts and bolts questions. Do you have to be careful about Twitter side API request limits or getting labeled as a denial of service attack? So does the cloud help mitigate this issue at all?
So that's a great question. Yes, there are several kinds of Twitter APIs, and some of them, they have the rate limits. So we have to follow those rate limits, and we cannot collect more than those number of tweets. But the second monitor, as we mentioned, using the COVID-19 lab endpoint, that is designed for especially for the academic and research use. So there's no rate limit for that endpoint. That means as long as there are new tweets posted online, we can collect them from the Twitter API. And that requires the even higher requirement for our monitor to handle the large amount of tweets.
I see. Cool. The next question we have, does the performance of these tensor-based methods rely on the presence of TPUs, or do they also perform better than the alternatives on GPUs and traditional GPU architectures?
Yasin, do you want to comment on that since you've been working with Danny on this?
Mm-hmm. Sure, thank you. So, when I was doing adopting the tensor-based LDA over GPU, so we were using TensorFlow library. So primarily the way it is developed is to enable the multiprocessing over CPU. And from our side, we are trying to do the same thing, but using GPU. Now, GPU, we are able to speed it up in multiple scale compared to CPU itself. So for example, the graph I shows the comparison about for LDA. It is a comparison between tensor LDA over CPU versus tensor LDA over GPU. So Mike has already explained that compared to the other method, tensor LDA can speed it up by a lots of problems, by a lot. However, GPUs was able to speed it up it much more. And for the reference library, it doesn't use any of the tensor. It uses just GPU and it is using CUDA cores. So I think this is your main focus about on the question. So we are using mainly CUDA cores from the GPU itself.
Yeah, CUDA GPU, got it. Yeah, okay, interesting. And I wanted to ask kind of a high-level question, which is you were sort of anticipating having this reaching a milestone in the near term for the software development and kind of the end use of this. Like if you were to extrapolate out to the future, do you have thoughts about the end users, the use of the output of this machinery that you're putting in place to analyze these streams of social media? Do you have a sense of where that where you would like to see that go?
Well, again, you know what one of our primary goals from our research perspective is toxic language and toxic behavior online, trying to easily and quickly identify that so that it can be dealt with in near real time. Whether that will be the end user of that will be the platform like Twitter, or it would be some other entity like us, or you know, law enforcement. It's hard to say. I hope that all of those become eventual kind of users for these approaches. One of the other researchers, an undergraduate at Caltech who's now going to Stanford for graduate school in CS, Maya Shrikant, presented a paper where she sort of outlined a way that you could use the results from this kind of machinery, this kind of architecture, to perhaps develop chatbots, where if you could identify quickly someone who's engaging in, say, racist speech or attack speech or some other kind of toxic behavior online, you could try to effectively intervene in near real time and say, hey, stop saying what you're saying, or, you know, the platform's going to remove you, or some you know, type of intervention like that. So, you know, I think that again, the end use here from our perspective is to try to clean up the toxic behavior that we see on these social media platforms. And those users could be academics, NGOs, law enforcement, the platforms themselves.
Well, I'm seeing in data science a lot of applicability to social good at University of Washington. So it's great to see this kind of potential developing. It's really going to be great to see where that goes. We have one other question in the chat. Is Caltech in this area working on projects with MIT CSAIL? And it mentions Sandy Pentland and others working on similar projects. So I think that's what does the community look like?
Yeah, not directly with that research group, although I in my other hat at Caltech is I am the co-director of the Voting Technology Project, which works directly with Ron Rivest, who's there. You know, there's a lot of research groups that are working in this area. And, you know, to date, we've been working primarily, you know, within Caltech to try to build up our group. But then we're now starting to reach out and to engage strategically with the social media lab at NYU, where we've got some research collaborators there and potential partners. And we're always looking for collaboration. So I don't know that MIT group very well, but I'm certainly going to be looking them up real quick.
Cool, doors open. Great. Well, our time is done. Thank you so much. This is really cool to see. And of course, it's such an engaging topic for all of us. So really appreciate the three of you coming and giving us this presentation. And with that, we'll take a break here, and we're going to be coming back at 10:30 so we can stop recording, and off we go. We'll see you in 10 minutes.